In this video lecture, I will discuss second order linear homogeneous recurrence relation with constant coefficient. So we now consider a method of solving a recurrence relation of the form Cn an plus Cn minus 1 an minus 1 plus Cn minus 2 an minus 2 is equal to 0 for n greater than and equal to 2, and where Cn minus 1 and Cn minus 2 are real constant with Cn not equal to 0. Okay, so now we have to learn how to solve the second order linear homogeneous recurrence relation. So what we will do, we will say that okay, an is equal to c into r power n. This value we will substitute here in this equation. For example, if I say this equation is equation 1, so for an we will substitute c into r power n in equation 1, and after substituting an is equal to c into r power n in this equation becomes, for an we have to substitute c into r power n. So Cn an is c into r power n, then Cn minus 1, and then an minus 1 will be c into r power n minus 1. Cn minus 2 and an minus 2 will be c into r power n minus 2. Okay, that is equal to 0 with c is not equal to 0 and r is not equal to 0. And then what we will do, this and let us say this is equation 2, and this we will divide by c into r power n minus 2. So if I divide this equation by c into r power n minus 2, we will get this Cn r square plus Cn minus 1 r plus Cn minus 2 is equal to 0, and this is nothing but a quadratic equation which is called a characteristics equation here. So once the recurrence relation of the second order will be given to us. So what we have to do, from the recurrence relation we need to write the quadratic equation, that is nothing but a characteristics equation. Once we get the quadratic equation, we all know how to solve the quadratic equation. So quadratic equation will have two roots, r1 and r2, and then the roots, there are three types of roots for the quadratic equation. r1 and r2 are real and distinct. Second case is when r1 and r2 are complex, and the third case is when r1 and r2 are real and equal. So in this video lecture I will discuss the first case when r1 and r2 are distinct and real. So let us take one example of second order linear homogeneous recurrence relation and see how to find the solution. Okay, so here this is the recurrence relation, an plus an minus 1 minus Cn minus 6 an minus 2 is equal to 0. Okay, so this is the recurrence relation, and you can see here this is the second order recurrence relation, and a0, the initial value a0 is given minus 1, a1 is 8. Okay. So when the case 1, when the roots are real and distinct, okay, we say that the an, the general solution, we know that when the recurrence relation is given to us, an is nothing but the general solution of the recurrence relation. So an will be a into r1 power n1 it's not n1 plus b into r2 power n. So this will be the solution of the recurrence relation, where r1 and r2 are the roots of the quadratic equation. Because from the given recurrence relation we need to find the we need to write the characteristics equation, that will be nothing but the quadratic equation, and we know that for quadratic equation there will be two roots, we will find the roots, and then the first case is when the roots are real and distinct. So if the roots are real and distinct, so there will be two roots, r1 and r2, and then we have to write an is equal to a into r1 power n, where r1 is the first root and r2 is the second root. So, and what is this a and b? This a and b are arbitrary real constants. Okay. So now let us take this example. So here from this, okay, we will write the characteristics equation. So in previously I have told from the recurrence relation how to write the characteristics equation. Using that we will write the characteristics equation or the quadratic equation. Okay, so it will be r square plus r minus 6 is equal to 0, and this r plus 3, this we can write it as r plus 3 r minus 3 r minus 2 is equal to 0. So the roots will be minus 3 and 2. So you can see here the roots are real and distinct. So what will be my an? My an will be this an will be c1 c2 also we can take a and b, anything. These are just the constant. So if I say c1 into r1 is nothing but -3 and r2 is 2, c2 into 2 to the power n. Okay, now if the initial condition is given, okay, why the initial condition is given? So that we can find the value of these constants c1 c2, or we can say a and b. If the initial conditions are not given, then we have to leave it here itself and this will be the answer. If the initial condition is given, next step is we need to find the value of c1 and c2, or we can say a and b. So how we will find? Suppose this is the equation 1. In this, if for n, in this equation, if I say n, if I substitute for n, if we put 0, I'll get, okay, a0 is equal to c1 into -3 power. I will say, okay, if I put n is equal to 0 here in this, I'll get a0 is equal to c1 into -3 power 0 plus c2 into 2 power 0. So anything power 0 will be 1. So this a0 is -1. So this will be -1 is equal to c1 plus c2. That only we got here. Okay, when we substitute n is equal to 0 in this equation. Same way for n, if I put 1, okay, if I put 1 in this equation, I'll get a1 for n is equal to 1. I'll get a1 is equal to c1 into -3 power n. So -3 power 1 because n is 1 here, and c2 into 2 to the power 1. Okay, so with that we'll get a1 is 8. So we'll get 8 is equal to -3 c1 plus 2 c2. Okay, so this is the another equation we'll get. These two we will solve and we get the value of c1 and c2. Once we get the value of c1 and c2, we have to substitute back the value of c1 and c2 in equation 1, and this will be the final answer. C1 is -2 we got, c2 is 1. So -2 into -3 power n plus 1 into 2 to the power n. So this will be the final answer of the given recurrence relation. So hope you have understood the concept. Thank you for